Why, hello. Today we're going to start Chapter 17, which deals with vector calculus. And in particular, we're going to be dealing with Section 17.1, which deals with vector fields. So you might ask, what is a vector field? Looking at the formal definition that they have in our textbook, it says, let D be some set in R2. R2 is the XY plane, okay? A plane region. A vector field on R2 is a function f that assigns to each point xy in D a two-dimensional vector f of xy. So for every point in two-dimensional space, the value of the function will not just be a number, it will be a two-dimensional vector. So as an example, here's the function f of xy equals y times I plus x times j. You can write your output of your vector by using I and j, your unit vectors, or you also could write it in vector form as y comma x. All right, so let's just find out some of the values of this function, like f. And notice I put a little bar over it because the value of the function is a vector. F of 0, 0 would be, since x is 0, the y coordinate is 0, and since y is 0, the y coordinate is 0. Okay, because notice it's yi plus xj. F of 1, 0 would be, notice the output is the vector yx. So since x is 1, the y component is 1, and since y is 0, the x component is 0. F of 2, 0 would be the vector 0, 2. F of, let's do 0, 1. I put the point 0, 1 in here. Since x is 0, my y coordinate is going to be 0. And since y is 1, that's going to be the vector 1, 1. F of 0, 2 would have output 2, 0. In fact, let's get some other points here. What if I wanted to look at like f of 1, comma 2? You get the idea with this particular function. It's the vector 2, comma 1. Now, a lot of times you like to represent this vector field. And the way you do it is the output of the function for 0, 0 right here is the vector 0, 0. Well, that's the 0 vector. So at 0, 0, its output's just the 0 vector, the vector that starts and stops at 0. At the point 1, 0, now where's 1, 0? 1, 0 is right here. F of 1, 0 is the vector 0, 1. It has an x component of 0, a y component of 1. So the output, the vector associated with the point 1, 0 is the vector 0, 1, whose x component is 0 and whose y component is 1. Let's draw at the point 2, 0, the vector associated with the point 2, 0. Well, that's 0, 2, which looks like this. Okay, the output at 0, 1, now where is 0, 1? 0, 1 is x component 0, y component 1. Its output is the vector 1, 0, which has an x component of 1, a y component of 0. And notice I'm drawing these output vectors with their tails starting at the point for which they're the value of that particular point. F of 0, 2, 0, 2's here. That's vector 2, 0. It goes like this. And finally, if I wanted to do f of 1, 2, notice 1, 2 is right here. I'll use another pen for that. That's the vector whose x component is 2 and y component is 1. Now notice if I put vectors at all the points, it would be quite messy and it would be all over the place. And you might think, well, why would anybody even want to do this? You know, what would you need this for? What could I use this for? Well, think about it. Suppose different things that we can use this for. In fact, let me just pull this up before we even do anything else to give us a little bit of motivation of what we're doing. Suppose I have a tunnel, all right? And the air is flowing through the tunnel. And let's just say this is two-dimensional, okay? I'm not going to do it three-dimensional right now. But maybe at this point right here, I would like to associate with the point, and maybe this is my y-axis, this is my x-axis. Maybe at this point, I would like the vector output for that to be the direction and the speed of the wind at that point. You with me? Maybe over here, the wind's maybe towards the edges, the wind's going a little bit slower. Maybe right here the wind's going faster. Maybe it's a little bit slower here. You could have at some points maybe you have a rock, all right, and then you're going to have at these points the wind flowing around the rock. You with me? So this would be of something that you would use a vector field for. In fact, some examples of what you want to use vector fields for would be force fields to show gravitational force. What's the gravitational force on an object, depending on where you are, okay? Wind velocity. They use this all the time when you watch the news, okay, when they're showing their little lines on how fast the winds are going. Ocean currents. Anything that has magnitude and direction as an output, depending on the location where you are, you would want to use a vector field to represent it. Now, right now, we're doing it in 2D. In a few minutes, we're going to be doing it also in 3D, because we do live in a three-dimensional world. So this is just a sort of a mundane example of notice what this function is doing. It's taking a point in R2, because you're taking a point in the plane, and your output, you could say, is also R2, because it's a two-dimensional vector. All right, if we wanted to do it in three-dimensional, we could say let E be a subset of R3. A vector field on R3 is a function f that assigns to each point x, y, z in E a three-dimensional vector f of x, y, z. Notice, my typist did not put an arrow over f here. She didn't put an arrow over f here because a lot of times the publishers, when they type, they make a bold-faced letter to represent a function. Now, when I write all the time, I'm not going to be pressing down real hard and saying this is bold, this is bold. I'll be putting an arrow on top of it. But a vector field's output is vectors. Here's an example of one. F of x, y, z is equal to 2j plus zk. In other words, now notice this is mapping it into three-dimensional space. Notice your x component is 0, your y component is 2, and your z component is whatever z is. So if I wanted to figure out what's f, and she should have a bar on top of that because she didn't make it bold, what's f of, let's say, 1, 0, 2? Well, 1's going in for x, 0's going in for y, 2's going in for z. So f at the point 1, 0, 2 would be the vector. Well, it's always 0 for x, it's always 2 for y, but the z component's just the z component. So it would be the vector 0, 2, 2. What if I wanted to find what's the output for the vector 1, 3, 5? At the point 1, 3, 5, the vector associated with it is x component's always 0, y component's always 2 for this particular function. Its z component is equal to z. Okay? What would be f of -2, 8, 12? The x component in this particular function is 0, the y component is 2, the z component is 12. Okay? Now, if I wanted to represent that, okay, just drawing a picture, and drawing a picture is not all that easy to do. Let me go back and show you. Now, let's see. I'm going to get, what's f of 0, 0, 0? That's going to be the vector 0, 2, 0, right? It's a vector here. I should make those sharp. X is 0, y is 0, z is whatever z is. So at 0, 0, 0, we have the vector associated to it that has an x component of 0, a y component of 2, because I'll use this in green, and a z component of 0. So at that point, we could, if you want, think of it as velocity. The wind is going that way. If I wanted to draw f of, let's do 0, 1, 2, okay, that's going 0 over 1 up to 1, 2, so we're going to be going up to 1, 2, right about there. That output is going to be the vector 0, 2, 2. If I wanted to draw that, I could do a little x, y, z right here. The x component emanating from that point is 0, the y component is 2, and the z component is 2, so it's pointing in that direction. As you can see, drawing these vector fields is a little bit difficult to do. You have to pick, you know, like, they would all be falling on top of each other if you did it for, you know, all the points, or even all the integral points. And by integral points, I mean where the coefficients are integers. So how can we do it a little bit better? How can we have a sense of how this wind is flowing, how the force is pulling us? What can we do? In this particular case, the computer's a real good thing to use. So let's go back and look at that initial example that we were looking at. Okay, I'm going to do this on Maple, all right? And you actually will have a worksheet where you're going to be doing this on Maple also. Also, if you look in your book and they have pictures of vector fields in your book, how did they draw them? They used either Maple or Mathematica or Derived. One of the major computer algebra systems is what they did. So first of all, I have Maple here. And I thought instead of me even loading up, I wanted to start out right off that you could see. The first thing I have to put in is with plots. So I type with plots, P-L-O-T-S. And I'm going to make this be a semicolon. If you're a novice to Maple, semicolons are better than colons because colons suppress the output. Notice, this is telling me all the wonderful commands I've just opened up that are now at my discretion to use. Notice there's 3 of them that we're going to be using today. One is called contour plot. That's right here, contour plot. We'll be using that one today. There's another one called contour plot 3D. We'll be looking at that one later today. The one we're going to look at right now is field plot. You do that when you're going from R2 to R2. Okay? When your vector field is R2 to R2. If you're going from R3 to R3, it's field plot 3D. That's if you're in a 3-dimensional world. And later on today, we're also going to look at, remember we talked about the gradient a chapter or so ago? It's going to be back. And we're going to be looking at the gradient. If we wanted to plot the gradient to the function at every point, or if we're in a 3D domain, we'll use grad plot 3D. So we've opened all of those. Now what I'm going to do is I'm going to go back here. I'm going to backspace, and I'm going to make it be a colon, just so that I don't have all these commands messing up my page. All right? Now, our function that we looked at a few minutes ago was f of xy equals yi plus xj. All right? yi plus xj. Okay? All right. Now, I'm going to go field. First of all, let me just show you one thing that you can do. Let's hit question mark. Because suppose, you're going to watch me and you're going to forget how to do it. And you go, gee, she said it's field plot, or I see that it's that command. Let me just go over a few things that you can do when you remember the name of a command, because you open it up with plots and you see it, but you forget the exact same syntax. I'm typing question mark field plot and hit enter. This gives you a help screen. And it's real good to read all this stuff, but what I do a lot of times is I just scroll down to the bottom and I look at examples. Look at this example right here. They're saying load with plots. Yes, yes, we did that. And look what they do here. Field plot. In fact, one thing that you could do is just highlight it. Okay? If I highlight it, I'm going to go up here to edit and tell it to copy it. And then I'm going to close that window and come back here and hit edit and paste it. And now that command's right there in front of me that I don't have to be toggling between 2 things. Now notice how this command works. Notice what they do. Field plot, parentheses. Remember, in Maple, you use the square brackets when order is important. You use that for vectors, if you're naming a point, anything in which the order that you're listing them is important. You use the italics when you're listing like multiple functions that you want to graph. So here, the x component, notice, is all of this. X divided by blah, 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 comma. Here's the y component. It's huge. Y, blah, blah, blah. And then they just have to say what x is ranging from and what y is ranging from. Okay? Now, I'm not going to use that one, but notice what I'm going to do. I'm going to go in here and say, oh, for the x component, I'm going to just hit backspace to get rid of it. And my x component was a simple y for the output. And my x component, and this is a trick, when you forget how to do something on Maple and you want to come back and use it. And the x component was x. And they're having x go from -2 to 2, y go from -2 to 2. I think my grid was going from -5 to 5, so I think I'm going to go -5 to 5. And now, what Maple does, when I was sketching those vectors, I was doing them with the exact same scale as I was using for plotting my points. And did you notice my arrows all fell on top of each other, and it looked quite hideous. What Maple does is it shrinks down the arrows, okay, by probably a multiple of 10, you with me? So that they don't fall on top of each other. So let's just hit enter. Why am I getting, oh, there it is. Okay, it was thinking. All right, and can you see it? There's your field plot. If you want to make it a little bit bigger so everybody can see it a little bit more, shrink it up a little bit, there you go. They're showing at each little point how the force is moving, or how the wind is moving, or how the currents are moving, and that's a graph of this function f of xy equals yi plus xj. Okay, pretty neat. Now, the other one that we just looked at a few minutes ago was a three-dimensional function. It was f of x, y, z equals 2j plus zk. Notice that's really x component is 0, y component is 2, and z component is z. So we're going to go down here, and we're going to type field plot, but it's 3D this time. Whoops. Get back here. I just bumped my mouse. Field plot, F-I-E-L-D, P-L-O-T, 3D, because I'm in 3D, parentheses, brackets. What's my x component? My x component was 0, comma. What's my y component? It was 2, comma. What's my z component? Z, bracket. Then you have to tell it what x is ranging from, what y is ranging from, and I'm just going to be picking, whoops, -5 to 5, and z is going from -5 to 5. Close parentheses, and every single command in Maple must end in a semicolon. Now that looks like a lot right there, but notice what I'm going to do is, first of all, I'm going to put a axes in. You can either put it on the inside or we can put it on the outside, and you can actually pull this a little bit and turn it different ways to see, like this is looking just from the y-axis there. That's just along the y-axis. I could swing it around this way and just look along the x-axis, and you can see how things are changing. And you can see this could be wind velocity or all kinds of things that are going on, and it gives you a sense of how things are moving in that space. So field plots give you the capability of representing motion in space. Okay? All right. Let's go back and review something. Last chapter, no, we just took the test on 16. This is chapter 15. We learned how to take the gradient of a scalar function of two variables. And notice what this does. When you take the gradient of a scalar function, notice you get a vector, because it's the partial of f with respect to x evaluated at the point x, y, times I, plus the partial of f with respect to y evaluated at the point x, y at j. And so, notice, if you have a scalar function of two variables, the gradient maps a point in R2 into a vector into R2. It's a vector field. Okay? Now, therefore, the gradient of f in a vector is a vector field on R2. And we call this function the gradient vector field. All right? Similarly, if your scalar function f, notice it's scalar, f of x, y, z is equal to gradient of f, which is partial of f with respect to x, I, plus partial of f with respect to y, j, plus partial of f with respect to z, k, gradient f is called a gradient vector field on R3. All right? Okay, now let's look at this. Find the gradient field of the function f of x, y, which equals x squared y minus y cubed. Now notice, f of xy is x squared y minus y cubed. That's a function that maps R2 into R. That is not a vector function, is it? It's mapping a point in R2, but when you're done, you have R. What's the partial of f with respect to x? Well, if I take the partial of that with respect to x, I hold y constant, and I just get 2x. What's the partial of f with respect to y? Well, now I'm holding x constant, so this is like a constant times y. So the partial is x squared minus, and the partial of y cubed with respect to y is 3y squared. Okay? All right, now, the gradient of f, therefore, is equal to, its x component is 2x, and its y component is x squared minus 3y squared. All right. Now, what they want us to do is they want us to plot the gradient vector field and the contour map of f all in one graph. And they want us to talk about how they are related. Now, does anybody remember what contour map was? We're not going to do this with pencil and paper. We're going to use Maple to do this for us. When we talked about the contour map of something, what we were looking at was level curves in the domain. So, If we wanted to do it with paper and pencil, we'd have to take x squared y minus y cubed, and we'd have to let it look at some constant like equals 1 or equals 2 or equals 3. And then when you notice, since the original function f of xy equals this, suppose, I don't know what that looks like, but suppose the graph of that looks like this. Suppose it looked like that. Then you realize every single point along this level curve, every single one of them, if you took that point and evaluated f of xy at that point, since for all of them f of xy was equal to 1, as you moved along that level curve, all of those points would have f of xy equal to the same value. That's why they're called level curves. Because if you think of z as your output, they all would have z being the same height. They would all be level. Okay? So what we want Maple to do is to draw level curves, which is called the contour plot, and then the gradients. Now, think back in chapter 15. What did the gradient do? The gradient at a point pointed you in the direction of maximum change for the directional derivative, right? Think about it. If I'm along a level curve, if I'm at this point right here, and I point myself in the direction this way or that way of moving still, walking along the level curve, how much is my function changing? If you're moving along a level curve, if you're walking along a level curve, how much does the function change when you're walking along that level curve? Not at all. So what's your directional derivative equal to? 0, huh? So if you go in the direction of the level curve, right, your directional derivative is 0, right? As you might remember, your directional derivative in the direction of the vector u was equal to the gradient dotted with the unit vector in that direction, right? Now guys, you just told me if I go in this direction, in the direction tangent to the level curve, what is the directional derivative going to equal? 0. If you have two vectors whose dot product is 0, what can you tell me about those two vectors? They're perpendicular. Lovely. The gradient would be perpendicular to that vector that's pointing in the direction of the level curve. So in other words, at this point right here, I can guarantee you the gradient's either going this way or it's going that way. It's perpendicular to the tangent line at the point of the level curve. So when I look at this, I'm going to expect to see, I'm not sure what these level curves are looking like. You know, you might have all kinds of little level curves going like this. And if I put the gradient, plot the gradient, at each point, the gradient better be think of like at this point right here, look a little tangent line, I got to be perpendicular to it. I'm not sure how long that gradient is. I have no idea what its magnitude is, but it's going to be perpendicular to the level curve because it's pointing you in the maximum direction of change. If you move in the direction of the level curve, you're getting change of zippo. All right, now, we could, but I decided not to. We could do this with paper and pencil, but I picked one that I can use. Well, let's use some of the technology. So how are we going to do that? All right, here's my function. All right, the two things that we're going to use are contour plot and grad plot. All right, and the function that we want to use it for is f of xy equal to x squared y minus y cubed. All right, now I want to go in and say, well, let's go back up here. And instead of the semicolon, I'm going to use a colon. Notice grad plot is right here. Grad plot. See, there it is, grad plot. And here is contour plot. Okay? Now we could guess what those were, but let's go down and say, suppose we forget. I'm going to type question mark contour plot, no semicolon, just enter. And notice here it tells me about contour plot and contour plot 3D. Coming down here, I'm just going to take this one right here. Oh, I don't want the whole thing. Just that one right there. I'm just going to highlight one command. I'm going to go up into Edit, tell it to copy it. I'm going to minimize that, come back here and paste it. And I have a command, a contour plot command. I go, oh, Contour plot just says, name the function, and then tell me what you want x and y to range from. So then I'm going to just put I'm going to click my little mouse at the end of that function, and the function I want to deal with was x squared times y minus y cubed. And I think I'd like it to go from -5 to 5. Oh, x squared. I didn't type a 2. Oh, I must have my numbers turned off there. Okay, so it's x squared, whoops, squared. X squared times y minus y cubed. And I want my x's to go from -5 to 5. And I want my y's to go from -5 to 5. And hit enter. All right, and those are my contour plots. Now, what does that mean? If I move along this line right here, if I move along that line right there, my f of x, y is a constant. If I move along any level curve, f of x, y is a constant on that line. All right, now, they want me to put the two on the same graph. So what I'm going to do is I'm going to suppress, now I'm not going to suppress the output. I'm going to name this plot something. Just pick anything. Usually you can't use D because it's for derivative, but I'm going to use A. In fact, I'm going to use A1. A1 colon. Now, you might find, like in your assignment when you get it, like for number 1, you can call them A1, A2, A3. Then for number 2, do B1, B2, B3. Don't use the same letters all the time, because then when you're moving around on your Maple worksheet, I'm sure you've noticed that things can get a bit tainted. Now notice, many of you have done this, but let me just hit enter right here. I'm assigning this graph to A1. Notice, when I hit enter, my goodness, what is it giving me? It's giving me all the points that it plots to give that output. There's a lot of them that it has to plot. You see all of them. Do I really care what that list looks like? No. It keeps going because there's multiple level curves, aren't there? So that's why you see when I tell you to assign a plot, I tell you to use colon because I'm asking you to suppress. It goes on forever. That's another level curve. Level curves take a lot of points to plot. I'm going to suppress it with a colon. Then I don't have to see what the output is. Now let's do grad plot for a second. Grad plot, G-R-A-D-P-L-O-T, means plot the gradient at all the points. I can be lazy here. What I'm going to do is highlight the function, go up to edit and copy it, come down here, go up to edit, and tell it to paste it. Also, you could type Control-V. That would work also. And, in fact, I want to go from -5 to 5 also. So let's go up to here, edit, copy. I could have done it all in one foul swoop, but I chose not to. Come back here, paste. There we go. Close parentheses, semicolon. All right, and that's the gradient field. That's showing me the gradient. The gradient of that function evaluated at every single point. Not every single point, but selected points. And also, this is a vector field. They're not drawing the vectors to scale. They're shrinking them so that they can get more into one graph. Now, I want to put this graph and the contour plot graph all in one graph. So what I'm going to do is I'm going to call that A2. And again, I do not want to see a list of all the points that it needed to plot to get there, even though it would be interesting. I'm going to suppress that with a colon. And then to put the 2 in one graph, I tell it to display. Now, I'm giving a list of 2 plots. The order is not important, so I use italics. A1, comma, A2, close italics, close parentheses, hit enter. Semicolon, hit enter. And look at that. Look how beautiful that is. Let me make it a little bit bigger for you to see. Oh, I want to go this way. Look at that. At every point, do you see how? In fact, let me go up to here and tell it to go 1 to 1. 1 to 1 makes my scale in the x direction and y direction be the same. As you can see, your gradients are perpendicular to your level curves. Because if you move in the direction of the level curve, you have 0 change. Perpendicular would give you maximum change. Not hard. Okay? All right, let's go on then. Definition. A vector field F is called a conservative vector field if there exists a scalar function f such that the gradient of f is equal to big F. F is then called the potential function of f. What we did a few minutes ago is we had a function here, f of xy equal to x squared y minus y cubed. Okay? We took the gradient of it, and that gave us a vector field. The question is this: if you give me a vector field function, can you find that function scalar f that if you take its gradient, you will get big F, the vector function? If that's the case, it's called a conservative vector field. Right now, you're looking at that and you're saying, I don't understand what she's talking about. What I'm saying is if you have some vector valued function, it could be 2D or it could be 3D. Maybe I have the vector valued function f of xy equal to x squared comma y squared. The question is, can you find some function z equal to f of xy such that the gradient of f is equal to the vector function big F? If that happens, if you can do this, if you can find this scalar function, we call f the potential, and we call big F a conservative vector function. If any of you have taken physics and you've studied the potential of various kind of forces, yes, they're one and the same. Okay? We're not going to do that today, but later in this chapter we will tie it together. All right, so if you can find some scalar function f that if you take its gradient, you get the vector function big F, we say that big F is conservative, and we call little f the potential of the function. All right, for homework, I want you to read pages 1091 to 1097, and then on pages 1096 to 1097, you should do this. Looks like a lot, but like 12 of them are matching. You're just looking at a vector function and you're mapping it with the vectors. I mean, you're matching it with the vector field that they drew. Try to do it with paper and pencil, just figuring out, oh, in this vector field, all of them have an x component of 1. So what vectors do I see all have an x component of 1? See down here, what you're going to be doing is you're going to be like matching these functions with these here. And you look like here in number 12, all of the x components are 1. So you look at that and you say, oh, which vectors all have an x component of 1? Or here, f of xy equals y comma x. Well, in that case, they're switching the y's and the x's and pick particular points and pick, if the vectors match up with what you got. If you're at a total loss, turn on maple, and then if you for sure can graph, you can match them. So there's like about 12 of them that are just matching. So we want to do 1, 7, 9, 11 through 18, all, 21, 23, 29, and 29 to 32. On Blackboard, I will post the even answers since they're not in the back of your book. All right, and I'll see you next time. Bye-bye.